When you upload a file, it is tempting to picture a destination that looks like this: an infinitely expanding, flawless, and indestructible physical hard drive, waiting to hold your data exactly as you left it. The engineering reality of cloud storage is completely divorced from that physical imagery. At scale, data storage becomes a highly fragmented, abstract mathematical space. To understand how this machinery actually operates, we are going to trace the life cycle of a single 1 GB binary file. Let's call it data.bin, starting from a standard API put request all the way down to its final resting place on physical silicon. Following this file will expose 3 distinct mechanisms operating beneath the surface. Mechanism 1, namespace flattening. Mechanism 2, parity generation. Mechanism 3, quorum consensus. The modern digital vault operates as a continuous cryptographic process, rather than a static physical fortress holding a complete assembled file. The journey begins the moment a client application executes an API put request, packaging the 1 GB data.bin file for transit. Milliseconds later, this request strikes the ingress node. This is the absolute outer boundary of the data center topology, the point of contact where external internet traffic meets internal infrastructure. The ingress node rips the file apart, separating the large geometric payload from its text metadata. Lightweight metadata routes instantly to the control plane. The heavy payload drops into raw storage. Traveling together, the heavy payload acts as an anchor, choking the system with latency. Achieving petabyte scale requires instantly decoupling what a file is from where it lives. Local computers use traditional hierarchical file systems. You place a file inside a folder, which sits inside another folder, creating a nested path. To find a file, the system must process inode lookup sequentially, reading step by step down the folder tree. At the petabyte scale, filtering through millions of nested folders creates cascading latency failures. The entire directory structure locks up. To solve this bottleneck, cloud infrastructure uses an entirely different architecture: object storage. Data.bin is stripped of its folder path and assigned a unique SHA-256 cryptographic hash. Folders vanish. This flat namespace functions as a single, infinitely wide layer with zero depth. When a request arrives, metadata servers use this hash to instantly pinpoint the target block. There is no path to traverse. A multi-step folder search takes exponential time based on the depth of the directory. A direct hash lookup executes in one operation, taking the exact same fraction of a millisecond, whether the system holds 100 files or billions. Completely abandoning human-readable hierarchy is a strict prerequisite for machine-scale retrieval speeds. The common assumption is that cloud providers ensure data safety by making 3 exact physical copies of every file, scattered across different servers. This chart shows the penalty of simple RAID 1 hardware mirroring. Storing 1 GB requires 3 GB of physical space. At exabyte scale, a 300% overhead is a financial and spatial impossibility. You must build, power, and cool 3 massive data centers just to hold one. Harsh economic constraints force systems engineers to abandon simple physical mirroring entirely. They rely instead on mathematical fragmentation. The required algorithmic solution to the 300% storage overhead problem is a mathematical process called erasure coding. The payload is algorithmically divided into exactly 8 equal pieces, known as data shards. The algorithm mathematically generates 4 additional parity shards. These 12 total shards are then immediately distributed across 12 physically isolated geographic server nodes. The core durability equation is strict. Out of 12 total parts, the system only needs any 8 shards to perfectly reconstruct the original file. This allows extreme disaster tolerance. 4 entire server racks can catastrophically fail and lose power simultaneously, completely destroying their local shards. When 4 shards vanish, an automated reconstruction triggers. The remaining 8 use parity data to instantly redraw the missing information. The new footprint is 1.5 gigabytes, not the 3 gigabytes required by physical mirroring. This cuts global infrastructure costs exactly in half. Actual durability in the cloud is achieved through calculated fragmentation, not physical duplication. Returning to our initial request, the 12 scattered shards are now actively landing on their respective physical disks across the data center. As each drive physically writes its shard, it generates an acknowledgement signal, an ACK, that must be sent back up the stack to the control plane. Because of network latency, cable lengths, and internal routing, some geographic nodes will confirm receipt of their shard several milliseconds before others. This introduces the CAP theorem constraint. Engineers must trade off absolute consistency, waiting for all 12 nodes, and immediate availability, keeping the system fast. This diagram demonstrates eventual consistency. The API returns a successful 200 OK message to the user, the exact millisecond a minimum quorum of 8 nodes confirms receipt. It does this even if 4 lagging nodes are still actively writing data. Perfect global synchronization must be intentionally sacrificed. If the system waited for the slowest drive to report back on every single transaction, the end user would experience crippling interface lag. Shifting perspective away from a single file, we look at the macroscopic scale of the entire global data center. The statistical reality of operating millions of spinning platters and silicon chips is that individual hard drives are physically failing every minute of every single day. Erasure coding parity algorithms are not just invoked during uploads, they are constantly running as a background service, autonomously sweeping the infrastructure for dead drives and mathematically rebuilding lost shards onto fresh hardware in real time. The digital vault is a living, continuously regenerating software organism, relentlessly repairing itself against hardware decay. To store a single file, the architecture extracts the payload, strips away the hierarchical folder, hashes the object, shatters it into parity shards, and distributes those shards across a flat namespace. This highly specific sequence achieves a measurable, standardized metric, 99.999999999